Okay, let's do a little quick recap, and then we'll look at this enthalpy change worksheet and do some examples. So we know this, that energy has a magnitude and a direction, okay? Now it turns out that one of the laws of thermodynamics tells us that heat only travels from hot places to cold places. It never goes the reverse direction. So if we set up a situation where we're showing heat move one way or another, those values are going to either be positive or negative depending on the way that they flow. If heat flows out of a reaction, its enthalpy change will be a negative number. If heat flows into a reaction, then we give the enthalpy change a positive number. So heat in gives me a positive delta H, and heat out gives me a negative, delta H, and we call the first one endothermic, and we call the second scenario exothermic. Okay, other things, they have a magnitude. So if I do a reaction that turns A into B, and that reaction is plus 100 kilojoules in enthalpy change, when I do this, oh, trouble with touching the tablet is sometimes I switch pages. I don't know if you could see that on your end. Energy is what we call a state function. It doesn't really matter how you got to the number is the number, okay? But if I double the quantity, then I should be expecting the energy change in terms of enthalpy, the heat change, to also be doubled. You know, if I burn one lump of coal, I should expect one lump's worth of coal's heat to be given out. If I burn two lumps of coal, I should expect that fire to be hotter, to give out more heat. All right? Here's the other thing. If I can make that reaction turn around and go the other way, that I can turn B back into A, magnitude stays the same, but the sign, the direction changes. Okay? Now there's a guy called Hess. And Hess put all of these things together and says that if you can construct like a roadmap of how your reaction works, then the overall energy change is the sum of all of the individual energy changes. So for us, Hess's law is going to be that the overall enthalpy change for a reaction is the sum of any smaller steps. If you can break a large operation down into smaller steps, and then you just add up the smaller steps, Well, that gives you the total that you had before. And we talked on Wednesday about a scenario where we could say, here's Austin, here's Waco, and there's Dallas. And because those are all on the I-35 corridor north, there is a direction here. And if we know that that is 90 miles north and that is 90 miles north, then Hess's law says the overall enthalpy change for this reaction is the sum of all the smaller steps, which means it's 180 miles north. You just add the steps together. Okay? Let's do the worksheet. I'll leave this up on the board for just a second. Yeah, Brianna. So Hess's law can be said a couple of different ways. One of the ways, and I think I wrote this on the board on Wednesday, is that the energy in a cyclic system is conserved. If you go around in a loop and you come back to where you started, then the total enthalpy change for a cyclic system is zero. The total enthalpy change for a cyclic system is zero. But in a smaller sense, what it means is that the overall heat transfer, the overall enthalpy change for any reaction is the sum of any smaller individual steps. So if you've got a process and you can break that process down into steps, then just add all the steps together and it adds up to the total of the big picture. Okay. Okay, let's look at this worksheet that I've posted to Blackboard. There are a number of questions on this sheet, and there are two types of question. So we're going to have to come back. We'll do one or two of these. We'll do a couple of these, and then we'll go back to the whiteboard. We'll introduce a new concept, and then we'll do one or two of the final questions. So the first 6 questions are Hess's laws questions, and the last 3 are something slightly different. Okay, this first question is the Austin to Waco to Dallas question, because it says, let's take a look, that this first reaction, I'm going to call this step 1. You take some phosphorus, you add some chlorine, and it makes PCl3. And then reaction number 2 says you take some phosphorus, you add more chlorine, and it makes PCl5. And the question is, what's the energy gap associated with this reaction? Okay, if I was going to write this symbolically, we'd say, here's P, and P can go all the way to PCl5. And that's this number 2. And it is negative 886 kilojoules. What does a negative number mean? Does that mean it's giving out heat or taking in heat? A negative value of enthalpy change. Yeah, that's an exothermic reaction. It's giving its heat out. And 886 kilojoules that's a pretty strong number. That's a pretty strong number. Okay. So we know that that is negative 886. And the other thing that's on the board is I can go to PCl3. And PCl3 is reaction number 1. And its energy difference, its enthalpy change, the amount of heat that it gives out, is 640 kilojoules. Okay. And look what the question is asking. The question is, start here, go there. The question is asking, what's that gap? So symbolically, this is about as straightforward as they come. We've given you the long distance, we've given you the middle distance, and we're asking you, if I stopped in the middle, how much further do I have to go before I complete my task? All right. So let's do that the sciencey way, because what we've got here are equations that the arrow is an equals sign. So let's use it that way. Okay, here's how we would do that. You look at the data that's given to you in the question, and then you look at what it is that you are being asked to find. And the thing that you are being asked to find has PCl3 as a reactant and PCl5 as a product. Now, if we treat our chemical equations like mathematical equations, you might remember from high school math, if you've got two equations with the same variables in them, you can add them together. You can sum those equations. So let's look at what that would mean. So I'm going to clear the board. I need to have PCl5 be a product. And in line 2, PCl5 is a product, only there's 2 of them. And I'm only being asked to find the energy gap, the heat loss or the heat gain, whichever way it turns out to be for one of them. I will do that at the end. Okay, I'm not going to fix that just yet. The other thing is that in my answer, PCl3, phosphorus trichloride, needs to be a reactant. And in the data provided in the question, PCl3 is a product. So what I need to do is this. This is line 1 and this is line 2. Line 2 can stay the way it is because the PCl5s line up on the correct side of the equal sign. But number 1 needs to change. So I'm going to turn number 1 into something that I'm going to call -1 that just says 2 PCl3 goes to 2p plus 3 Cl2s. So I've taken line 1 and I've reversed it. And what that does is it lines the PCl3s up on the correct side of the arrow. Okay. What would the enthalpy change for line -1 be? It is a positive value. It's positive 640 kilojoules. Yeah, very good. So we've taken the value for the enthalpy change of number 1 and flipped it. When I turn line 1 backwards, everything changes. The magnitude doesn't change, but the direction of that energy changes. So it goes from being negative to being positive. Okay, let's write everything down and see if we can make sense. So now I have line -1, and I'm going to add line 2 to it. And line -1 says 2 PCl3s makes 2 Ps and 3 Cl2s. And line 2 says 2P plus 5 Cl2s makes 2 PCl5s. Okay. I'm going to add those together and see what I get. Now in math, if something appears on both sides of the equal sign, then you can cancel it. Those phosphoruses appeared on both sides of the equal sign. What else can cancel? See this PCl3? Only appears once on the left-hand side and doesn't appear at all on the right-hand side, so it can stay where it is. These chlorines, Cl2, I have 5 of them on the left. Oh, and I've got 3 of them on the right. So 3 out of 5 can cancel. All 3 of those are gone, and it leaves me 2 chlorines behind. So when I add line 2 and line -1 together, it's the same as subtracting line 1 from line 2. I get 2 PCl3 plus 2 Cl2s equals 2 PCl5s. And the enthalpy change for that would be, the enthalpy change for that would be, let me just click. The value for line 1 is plus 640. The value for line 2 is negative 886. Add those two numbers together, what do you get? Negative 246 kilojoules. Coles, it's a really good answer. You've given me the sign, you've given me the magnitude, and you've given me the units. So this turns out to be negative 246 kilojoules. Is that my answer? It feels like I've done quite a bit of work. That should be my answer by now. But it's not quite, because that's not what the question asked for. The question asked you to find the value for when one PCl3 reacted with one chlorine gas to make one PCl5. And you've found the energy for 2 moles of PCl3 and 2 moles of chlorine and 2 moles of PCl5. Yeah. I'm just going to divide everything in half. So 1 PCl3 plus 1 Cl2 going to 1 PCl5 is negative 246 over 2, which is 123 kilojoules in the negative, exothermic. Okay? Should we do another one? Okay. Look at the wording, the phraseology in question 2, and you'll see that's another Austin, Waco, Dallas question. It says, this is the energy to turn xenon into xenon difluoride. This is the energy to turn xenon into xenon tetrafluoride. What's the energy to turn xenon difluoride into xenon tetrafluoride? This is the same question as question number 1. Okay? It is the same thought process. I'll not do that one. Question 3 looks a little bit more involved because it's got more things in the equation. Okay, there are more things in the equation now, so there are more things to distract your attention. This looks more threatening, but all of these reactions, all of these examples are largely the same. And I've got 4 ammonias. Let me pick the pointer. I've got 4 ammonias here and 4 ammonias there, and some oxygens, and then, oh, they make different products. They both make lots of water, but one makes nitrogen monoxide and the other one makes dinitrogen. And the question asks, what happens? Can you use all of this information to find this information? And yeah, absolutely we can. And notice that the information that we're being asked to find, nitrogen plus oxygen makes 2 nitrogen monoxides, doesn't include anything at all of these waters. Those waters don't appear in my answer. Well, look, they're equal amounts. I think those numbers are destined to cancel each other out. And these ammonias, I've got lots of ammonia in this question, but I got no ammonia in my answer. I think those ammonias are going to cancel each other out. Okay, let's do this one. Going to call the top one line 1. I'm going to call the bottom one line 2. Here's my question to you folks playing along at home. Line 1 or line 2? Which one do I have to reverse? Yeah, very good. Very good. Specifically loving the way that you all chime in at exactly the same time. Megan, you got the right answer, but not the right reason. Reason is this. When I look at how I have to phrase my answer, nitrogen is a reactant. And when I go and I look through the data presented to me in the question, here's an ammonia, there's an oxygen, here's a nitrogen monoxide, there's a water. There is no nitrogen in line 1. The only time that nitrogen shows up is an ammonia, there's an oxygen, there's a nitrogen. It's in line 2, but it's a product. It's a product in line 2, which means I have to make it go across the equal sign. I have to flip line 2 to make it match what the question is asking me to find. My answer has nitrogen as a reactant. The data in my question has nitrogen as a product. So line 2 has to get reversed. When I look at the other thing that's in the question, nitrogen monoxide, nitrogen monoxide is a product in the answer and a product in the data in the question. So line 1 gets to stay the way that it is. Line 2 has to get flipped and reversed. Okay? So let's do that. I'm going to take line 1, which is 4 ammonias and 5 oxygens, making 4 nitrogen monoxides and 6 waters. And it has a value of -1170. That's a big number. And negative. Remind me what negative means? Exothermic. Gives away its heat. Yeah, very good. All right. And then line 2 has to get flipped. So I'm going to write the reverse of line 2 out. And it is 2N2 plus 6 H2O makes 4 NH3s and 3 O2s. And its enthalpy change value is now what? That's plus 1530. Yeah, and these are in kilojoules. All right, let's add line 1 and negative line 2 together. And here's how we do that. This ammonia, I got 4 of them. 4 of them on the left and 4 of them on the right. They got to go. All 4 of those ammonias just canceled each other out. These waters, I have 6 waters on the left, 6 waters on the right. They canceled. And I have 3 oxygens on the left and 5 oxygens on the right. So that canceled. Well, 3 out of 5 of them canceled. And then that leaves me this. That 2N2 plus 2O2 makes 4NO. What would the enthalpy change for that reaction be? Take the enthalpy for line 1 and add the reverse of line 2 to it. Okay. I have two people saying a positive number. I'm taking a small, it's a big negative number, but I'm adding a bigger positive number to it, which means that my final answer goes positive to the value of plus 360 kilojoules. But look, the question asks us to have one nitrogen and one oxygen making two nitrogen monoxides, and I found the value for 2, 2, and 4. So I'm going to divide this by 2. And my value is half of 360. And half of 360 is 180. Okay? All right. We know how to do these now. We know how to do these. Very good. Thanks for the thumbs up. So I'll leave that on the board for just a minute. I'm going to go back to the whiteboard and introduce a new concept and find the enthalpy change for a reaction a different way. And what I said earlier, enthalpy is something that we call a state function. It's a number that exists, and that number doesn't matter what direction you come from in order to get that number. It doesn't matter how circuitous a path you got to get that number, which is how Hess's law works. And so there's another way that we can figure out what the enthalpy for any individual reaction is that we can just look at all the bits and pieces, all the reactants and all of the products separately in a reaction and find out how much heat did it cost us to make that material. That's something called the enthalpy of formation. And enthalpies of formation, they're all in the back of the textbook. We're a couple of hundred years into modern chemistry, quantitative chemistry, where stuff was measured. Quantitative chemistry happened right around the French Revolution. In fact, one of our very, very early analytical chemists was executed during the French Revolution because he was a tax collector and he invented very, very precise ways of measuring things, and it cost him his head because, you know, no one likes the tax collector. All right, so I'm going to deviate from this for just a second, and I'm going to go back to our whiteboard. Come on. Back. All right. Oh, I'm writing in red. Won't do. So there's something called the enthalpy of formation. You can ascribe an enthalpy to almost anything. If there is a heat transfer associated with your process, you can ascribe an enthalpy change to it. So there's a thing called the enthalpy of formation, which is the heat gained or lost, because we don't know whether it's going to be an endothermic or an exothermic process yet. When 1 mole of product is made from the elements in the standard state. Having a little trouble with the screen. Okay, so if I wanted to know what the enthalpy of formation of carbon dioxide was, I would take some carbon, which is a solid, and I would take some oxygen, which is a gas. Here are my elements. And I would combine them to make carbon dioxide to gas. And I would measure that. And then, being the good scientist that I am, I would share that with the world. Now, if I did my reaction under different conditions than you did, oxygen's a gas, carbon dioxide's a gas. So my answer is going to be subject to pressure and temperature. If I did my reaction under a different set of conditions than you did, then we would have different sets of numbers. So what we're going to do is standardize this. And a standard enthalpy, hold on, I have to close this window. A standard enthalpy of formation has this little zero above the H. And a standard enthalpy of formation is the heat gained or lost when 1 mole of product is made from elements in the standard state at standard temperatures and pressures. And I'm just going to say this out. I'm not going to go down the rabbit hole of that. At 25 degrees Celsius and 1 atmosphere. Okay? So if we do all of our experiments at room temperature and at atmospheric pressure, then everybody gets the same number. Our numbers are reproducible, and they can go into an appendix at the back of the book. And Appendix C at the back of the book is several pages long and contains masses and masses of standard enthalpies. And that's only for the common molecules that we use in General Chemistry 1. If you want to know the enthalpy of formation of anything, you can look it up online. These experiments have already, no, Megan, we never make you memorize numbers. Even if it's an important constant, it will be given to you. No memorization of numbers. All right. So if A plus B makes C plus D, then the enthalpy change of reaction under standard conditions is this threatening math-looking symbol, which is a sigma, and it just means sum. It just means add them up of all of the enthalpy formations of the products minus the sum of all of the standard enthalpies of formation of the reactants. These numbers are in the book. Here's the asterisk. If you are looking at an element in its standard state, I'm not going to say standard, I'm going to say natural. So oxygen as a gas has an enthalpy of 0, enthalpy of formation of 0, because you didn't have to try to make it. Nature already made it for you. You did not have to put any energy in or get any energy out by making the oxygen. It was already made. Okay? Let's go and apply this new knowledge to one of the questions at the end of that worksheet. Okay? So this enthalpy change for our reaction is the enthalpy of the products all summed together minus the enthalpy of the reactants all summed together. Megan, I think I don't know. I can't remember what deadline I set for it. I will look at the end. It will tell you on Blackboard. I will look at the end. Okay. So I'm going to go back to sharing the worksheet. Oh, all right. Well, hey, that's useful. Can I have it last year? Yeah, yeah. So let's look. Questions 7, 8, and 9 are these standard enthalpy questions. And here it says, look, find the enthalpy of this reaction, but it's got a little raised 0 right there, little O. That's the standard. Yeah, I think Riley, my intention was to have it probably be Wednesday. I'll have to check that the deadline is right. Okay, so these are my reactants. These are my products. And when I look, I've got standard enthalpies of formation right here in a little table. What's missing is the standard enthalpy of formation of oxygen. Here's oxygen. I've got 7 of them. Well, that value is 0. Okay. So the standard enthalpy of reaction, I'm going to need more space than that, is I'm going to erase everything and start fresh because I'm going to need some space. The standard enthalpy of reaction is, I've got 4 nitrogen dioxides. So I'm going to need 4 times the value of the enthalpy of formation of nitrogen dioxide. To that, I'm going to add 6 times the standard enthalpy formation of water. This is water as steam. Got to read the equation, because you might be asked to take these numbers from a table, and then I'm going to subtract from that 4 times the standard enthalpy of formation of ammonia, and then add 7 times the standard enthalpy of formation of oxygen. So this is 4 times 33.2 plus 6 times negative 241.8, and I'm going to subtract from that. This is where it gets a little bit tricky, because you've got negative numbers adding to positive numbers, and then you're subtracting other numbers from it. So keep everything clean. 4 times negative 45.9 plus 7 times 0. And I could do one of those calculations in my head. I know that 7 times 0 is still 0. My advice to you here is write it out. Write it out on paper before you go just diving straight into your calculator. Write it out. Make sure that you have the correct sign for each of these individual terms. So 4 times 30, this is about this first term is going to be about 130. And then 6 negative 250s, that's 1,500 negative. So this is going to be a negative number. And then I'm going to subtract another number from it that is also going to be negative. So I have a big number that I'm subtracting another negative number from, which is going to make my initial big negative number less negative. Anybody come up with an answer yet? My key tells me that this is negative 1134.5 kilojoules. I'm not sure we're allowed to have that many units of significant figures. Yeah, not supposed to have that many. That's just a number out of a calculator. All right, so the exam does contain one of these questions. Just add the numbers together. Sit down, take your time, make sure that your reactants are on one side, that your products are on the other. Going to leave the exam open the entire weekend. Plus, I'm going to allow it to run into early next week as well, for those people who just are having a time reacclimatizing because it's been a stressful recent time. Okay. If you have the ability to take the test over the weekend, I think I would be inclined to take it. What happens is if you let it drag out, you know, now you're in the middle of another work week and you've got other obligations to take care of. But yeah, I'm going to give you lots and lots of time to take this particular test. Katie, go ahead.
Hi, I did have a question. So, is the exam covering all of chapter 4 and then up until like 5.2? I'm just trying to figure out what material to study.
Yeah, all of 4 and essentially all of 5, because 5 is just exothermic, endothermic, that Hess's law, which we did a couple of those today, and then this thing on standard enthalpies. If this last thing looks a little bit daunting to you right now, I can tell you that experience shows me that once this clicks for students, students do really well on this question. It just looks like, oh, good grief, there's a lot going on the page. But it's just adding numbers together and subtracting numbers. So yeah.
Would
4 and 5.
there anything you recommend for like studying or anything other resources that would help?
Let me go back to.
I was also wondering,
How much in the old exams? Yeah, okay, so hold on, I'm going to share the screen with you. If I navigate away from this and I share the screen, Chrome tab, exams, share. There is a folder in Blackboard at the bottom of the content part below exams that says old exams. And these are exams from a couple of years ago.
yeah.
And that would be a good place, I would think. When you open one of these, you'll see that these were written as a sit-down paper test. And that paper test has, oh, look at this, it's got a table of standard enthalpies of formation on the first page. That tells us that one of those standard enthalpy questions is coming. And then a bunch of multiple choice questions on, look, oh, acids and bases, combining solutions and making a precipitate, enthalpy of formation being 0, and then some calculations. What one is that? Theoretical yield. We're past that. We did that earlier. Standard enthalpy change. Hess's law. So yeah, I would do the old exams. There's a folder, there's an entire folder of them.
Yeah, that sounds good. I'm also gonna ask you when your office hours were, just so I could like get a couple clarifications on
So
certain.
I do a virtual office hour that is Monday, Wednesdays, and Fridays at 11 back here in the Collaborate section of 1341.
Okay, so it's Monday, Wednesdays, Fridays at 11 to 12.
Yeah.
Alrighty.
Yeah,
That
and
helps a
not enough
lot.
people take me up on it. So I am, you know, it's all, the window's always open and not everybody chimes in. I've got a couple of nursing students who talk to me, but yeah,
Do I have
I
to
welcome
like make a
more people
scheduled
to do
appointment
that.
or can I just kind
No,
of like show up?
just show up.
Alrighty, that sounds really good. Thank you so
Yeah.
much. I'm trying to find resources to be able to study for your exams.
Okay. All right,
Alrighty,
good.
good day.
All right. Bye, everybody. Let me know if you have any trouble with the test, because you know Blackboard's a bit iffy. And I'll see you Monday.